Hello, everybody. Welcome to another live stream, this time with the audio enabled. In today's live stream, we're going to talk through what happened on Monday with Facebook. Now, I'll throw out there, I don't actually work for Facebook, so I can't really tell you objectively, definitively what actually happened that day. But I did see some interesting things from my corner of the internet, and the point of this session is simply to use the Facebook outage as a teaching tool to teach you guys about DNS, Anycast, and BGP. We'll get started in just a minute. If you have any questions, please hit me up in the chat room rather. And yeah, we'll get started pretty soon. Thank you for joining. Hello, everybody. Welcome, welcome. So the timer just expired, so we are about to get started. As most of you are aware, Monday, Facebook had a huge outage. I think they were down for something like 5 to 6 hours. It was an interesting, as a network engineer, it was very interesting to see kind of what happened and what different symptoms I saw about the outage from my corner of the internet. And then randomly on Tuesday, I posted to my YouTube page. I was like, "Hey, who would like to see a kind of a debrief of what happened with the Facebook outage?" And we had something like 300 responses saying they wanted to hear what happened. Appreciate that. Appreciate the engagement. So here we are talking through what happened to Facebook on Monday. Monday, yes. Now, I do want to throw out this disclaimer. I don't work for Facebook, so I don't actually know what happened. I wasn't behind the scenes. I wasn't working on the front lines, if you will. So all I can really explain is what I saw from my corner of the internet and what I saw reading through various other technical resources, we'll call them, also trying to figure out what was going on. So my plan today is not necessarily to explain objectively the full truth and the full story of what actually happened with Facebook on Monday. Instead, what I want to use is the outage that Facebook occurred to teach some very interesting topics that I've been meaning to teach in more depth at some point. And so I figured this might as well take it out for us. So the point of this lecture is essentially to talk through DNS, BGP, and Anycast to show you how all three of those things contributed to the outage with Facebook. Now, again, since I don't work for Facebook, I don't have the ultimate truth. So I'm going to be making assumptions and simplifying things in a lot of way to communicate some rather technical points to a wider audience. So hopefully you guys enjoy it and can get a lot out of it. With that said, let's get right into it. Have I been muted this entire time? Did I just do this entire thing on mute? I think I did. Can you guys hear me okay? I think I can. Oh no, I definitely did this entire thing on mute, didn't I? Oh boy. No, no, I think I did do this on mute. So I'm gonna start this over, and I'll edit this out in post, but that's kind of fun. Can you guys hear me now? Mention something in the chat room if you guys can hear me now. All right, well, we'll edit this in post. Okay, take two. This time, this time with audio. So, if you were with me for the last 10 minutes, I went off, started this whole thing on mute, and so now I'm gonna have to start over off mute. I apologize for the tech difficulties. It happens. Either way, the purpose of today is to talk through what happened with Facebook Monday during their outage. So, as most of you are aware, Facebook had a huge outage on Monday. They were down for something like 5 hours. I think they themselves said that it was their biggest outage in some number of years or whatever the case. Um, I don't work for Facebook, so there's no way for me to know objectively what actually happened that day. All I can do is tell you what I saw from my corner of the internet and from reading the different guides and networking resources that I'm a part of that all kind of contributed some facts to what actually went down. Now, the purpose of this lecture isn't to give you the objective official truth about what happened on Monday. The purpose of this is to essentially use their outage and use what I saw during their outage to talk through three really interesting topics: DNS, BGP, and Anycast. So that's the purpose of today, is to simply talk through these items. Um, can't believe I started this on mute. Okay, with that said, let's just get right into it. I'll fix this all in post. All right, so most of you are aware of DNS as the service which maps a domain name to an IP address. But DNS actually does so much more. DNS is actually a distributed database of a bunch of different mappings of a bunch of different things. The most common one, of course, is mapping a domain name to an IP address. Now, the way it works is a DNS server is going to have the answers, have all the mappings that are in store, and a DNS client is going to be asking for those various mappings. The client can take the form of anything like a laptop, a computer, a smartwatch, smart television, anything that's going to have to resolve some sort of domain. Now, a domain, I didn't really officially mention it, is anything that looks like this, anything that looks like what you would type in to a web browser when visiting the web. Now, most notably, notice that other DNS servers can also be clients and ask other DNS servers answers. So all of these clients are simply anything that's asking a DNS question. Well, I'm not having a good tech day, am I? I enabled the microphone, but I disabled the screen share. Oh man. All right. Well, I wish I could just start over, but it is what it is. Tech difficulties happen. So back to it. DNS is simply a mapping of a domain name to an IP address, but it's actually a bunch more than that, and that's what we're going to get into. So the way it works is a DNS client, something like a web browser, a computer, whatever the case, is going to make a DNS request, ask for an IP address for a particular domain, and then the DNS server is going to provide the answer. Now, this is what DNS is most commonly known for, providing an IP to domain mapping. But DNS does actually so much more. There are many other mappings that DNS can actually provide. The specific mapping of a domain name to an IP address is what's known as an A record. An A record, by definition, is an IP address to domain name mapping. But there are other things that DNS can provide, namely what's called a NS record. It's a mapping of a domain name to a DNS server. Now, the reason you would want a NS record is to do what's called delegation. I told you that DNS is a distributed database. What that means is that there's a lot of different servers that are all working together to serve the answers to every domain that ever exists. If you think about it, there's millions and millions and millions, possibly trillions of domains that exist out there. And it's unlikely or really impossible for a single DNS server to have all the answers of all the A records for every single DNS, domain out there. So the ability to delegate questions to other DNS servers is crucial, and the NS record is what does that. The way it works is a DNS client can make a request to a DNS server, and if this DNS server doesn't actually have the A record that the client is asking for, the DNS server can respond with an NS record saying, hey, listen, I don't have the answer, but this other DNS server does have the answer. Try there. So that's the purpose of an NS record. It allows a single DNS server to, in a way, redirect or send a particular client to a different DNS server. Now, DNS itself has many more records than just those two, but for the sake of understanding Facebook's outage, these are the two that you really need to know about. With that said, let's continue. So let me show you in more detail what actually happens with DNS. So DNS involves a conversation with a DNS client and a DNS server. But there's actually many different DNS servers that exist. There's actually 4 types of DNS servers that exist. The DNS server that most of us are familiar with is what's referred to as a caching name server, also sometimes referred to as a recursive name server. This is the type of DNS server that you configure on your client. So if you are booting up a computer and you're configuring IP addresses and you're configuring a DNS server, you're configuring an IP address to what's known as an IP address of a caching DNS server. If you use Google's public DNS or Cloudflare's public DNS, those are caching or recursive DNS servers. These are just 2 different terms for the same thing. On a Windows box, you can actually see the DNS server by typing ipconfig/all. So this right here is my IP address, and then these down here are my DNS servers. These DNS servers, these IP addresses, are the caching name servers for this particular, for my laptop right here that I'm doing this stream from. On a Linux box, cat etc resolve, you can cat out this file to show you the IP addresses of that particular, of this VM's caching DNS servers. The way it works is me, the client, my laptop, is always going to make a request to just the DNS servers that I have provided. And then my caching name server, if they don't have the answer, they're going to go and figure out the answer on my behalf. So they're doing all the work on behalf of me, the client. Now, how they go through it is actually pretty interesting. And this is where the other DNS servers come into play. The first of the other DNS servers that we're going to talk about is the root DNS server, or root servers. There's actually 13 of them. Each of them are given a letter, A through M, and they're each managed by different nation states or different huge ISPs, and they're Anycasted all over the world. And we'll talk about Anycast later on in maybe like 15 minutes or so. In any case, this is the start of the DNS hierarchy. All DNS queries, all DNS resolutions are going to start with a resolution attempt for the root DNS servers. And I'll show you that in a moment. The next type of DNS server that I want to introduce is the TLD servers. TLD stands for top level domain. A top level domain would be something like .com, .net, .org. Think of it as the far right of any IP address or any website. And then finally, the last type of DNS server we want to introduce is the authoritative, or the authoritative name servers. These are the name servers that have all the A records for any domain that I'm trying to look up. So remember I told you earlier that an A record is a mapping of an IP address to a domain. So when me as the DNS client is trying to look up the website practicalnetworking.net, what I'm looking for is the A record for practicalnetworking.net, and that's going to exist on the practicalnetworking.net authoritative name server. Now, what will happen is my client is going to make a request to the caching name server, and if the caching name server doesn't have the answer, it's going to go and ask all of these sequentially to find the answer on my behalf. So here is how that works. The DNS client is going to initially make a request for a particular domain, in this case facebook.com, to my caching name server. Now, if you think about it, I said earlier, the caching name server could be something like 8.8.8.8, right? Google's DNS server, which means millions of people are making requests to the caching name server, which means it's unlikely that I am the first person to make a record request for facebook.com. So most of the time, the caching name server already knows the answer and can just provide it directly back to my DNS client. Each of these answers that we're going to show you in a moment is held onto for a certain amount of time. It's stored in cache. That's why this is called a caching name server, because it's going to make a bunch of requests for a bunch of different users, a bunch of different clients, keep all that information in cache for a time period, and then if other users are asking for the same domain, it's going to simply just give them what they already know. Now, I want to show you the full DNS process. So we're going to pretend that this is the first time anybody has asked for the domain facebook.com. So my DNS client asked for the IP address for facebook.com. My caching name server then forwards that IP address essentially to the root name servers. The root name servers are going to come back with a NS record telling me, hey, I don't actually know, the root server saying, I don't actually know the IP address for facebook.com, but go ahead and try the .com TLD name server. This will then prompt my caching name server to make a request to the TLD name servers, asking them for the IP address of facebook.com. They will then respond with a NS record saying, hey, listen, I don't actually know where facebook.com's IP address is, but you can try Facebook's authoritative name server, which will then prompt my caching name server to ask for the IP address for facebook.com from the authoritative name server for Facebook, who finally has the answer that I'm looking for, and then the caching name server will forward that along to my DNS client. From the DNS client's perspective, I asked the question and I got an answer. The DNS client has no idea that all of this over here is happening. It's removed from that process. Now, in each case, every single one of, so there's what, four different question and answer sessions. In each case, a caching element happens, if you will. Meaning, when my caching name server makes a request to the root name server, and the root name server comes back with the TLD, the IP addresses of the TLD name servers for the .com TLD, my caching name server is going to hang on to that for a period of anywhere from like a few minutes all the way up to like 2 or 3 months. The idea is think of how many requests these caching name servers have to make. It doesn't make sense for these caching name servers to blast the root name servers all the time, every day, every few seconds, millions of times a minute or whatever. Instead, it's going to make the request once, and it's going to hold on to this answer for a period of, a couple minutes all the way up to 2 months, however long it needs to, however long it's configured to. Also, however long it's indicated to hold on to that record in the actual NS record response in a moment. I'll show that to you in a second. This is how the load for DNS, if you think about how many DNS clients exist out there, there's billions of devices that are connected to the internet. They're all making requests to various domains. That doesn't translate to a single request to the root server every single time. This caching name server makes the request once or twice, rather once, gets the response, caches that for a while. Then the caching response name server makes a request to the TLDs, gets a response, caches that for a while, and so on. So at each level of this, there's some distributed saving of the information, which further ties back to what I was saying earlier about DNS being a distributed database. Now, I want to show this to you. So if I go back to my Linux terminal over here, I can use the dig utility to make a DNS request. So facebook.com. Notice I made a dig request for facebook.com. Dig stands for, I believe it's domain internet groper or something along those lines. Either way, it's a DNS troubleshooting tool that comes with all Linux boxes. When I type dig.facebook.com, my client, my Linux box, made an A request. I'm going to go back a second. Essentially did this. Sent a request to a caching name server and then received a response. Notice my response was an A record. That's what that A record comes into play. The A record is a mapping of a domain, in this case facebook.com, to a IP address, Facebook's IP address. Now, I can tell my client, if I go back over here, I can tell my client to act as a caching name server and do all of this. And I want to do that to you to kind of prove prove the order of events that I showed you in my slides. To do that, I'm going to use the exact same command, facebook.com, but I'm going to offer the trace option. This is going to tell my client, my Ubuntu box over here, to step through the full DNS resolution process. I'm also going to add another option, no DNSSEC. That's going to disable DNSSEC, which is a whole other set of lectures that I could go into, but for now we're going to disable it just to keep things a little bit more simple. Cool. So if I hit enter, you'll see it kind of step through its sequence. Awesome. So let's talk through what's going on. So here's the command that I ran, right? And notice that the first thing it did was reach out to the root name servers. Remember I told you there's 13 of them, and they own the letters A through M. There you have them right there, right? So like there's your A root server, there's your, where's B? Your B, your C, your D, your E, F, G, H, I, J, K, L, and so on. So this is the start of the chain, the top of the DNS hierarchy, if you will. Then my client made a request to one of these to figure out the TLD name server IP addresses. Notice down here, this next set of answers, which are all TLD name servers, the next set of addresses I received from m.root.servers.net. That's this guy right here. So of the 13 name servers, my client didn't need to talk to all of them. It needed to know all of them, and then it picked one of them to make the next request to. So it made the request to, it looks like in this case, the m root server, name server, and then the m root name server came back with these answers. Was like, notice these are NS records. So the m root server was like, I don't know the IP address for facebook.com, but try asking one of these TLD name servers. If I scroll down a little bit further, we'll see that the next set of responses came from f.gtld.servers.net. That would be this guy right here. So this one this one server my client reached out to and was like, hey, what's the, and responded by saying, hey, I don't know the IP address for facebook.com, but try the facebook.com authoritative name server records. That's what this set of answers are showing you. Now notice there are 4 authoritative name servers for Facebook. I want to point this out to you to show you that the name servers are redundant, meaning if one of these fails, theoretically the other ones can take the place and continue resolving DNS queries made to facebook.com domains and subdomains. I'm pointing this out to show you that there is redundancy at the DNS layer for the Facebook authoritative DNS servers. But something else other than a mere DNS failure is what actually happened on Monday, which caused access to these DNS servers to fail. And we're going to unpack that